Electronegativity is the ability of an atom to attract or pull the electrons it shares with another atom towards itself. And you might be wondering, why do I need to know electronegativity for organic? Extremely important, right? When you write reaction mechanism, it becomes very important because electronegativity will help you understand the regions in a molecule where you have high electron density and low electron density. And trust me, if you can recognize the regions that are high in electron density and low in electron density, you will be able to easily understand your reactions with all functional groups, whether it's alcohols, alkenes, etc. So electronegativity is important for organic because it really will help you when you start writing reaction mechanism, when you start looking at reactions with all the different functional groups. Now, your electronegativity as it relates to the periodic table, let's talk about this a little bit. You will remember from Gen Chem, or if you don't remember, it's fine. Your electronegativity will increase as you move across a row and also increase as you move up a group, right? And it increases as you move from left to right. The elements that are found on the right side of the periodic table are higher they're the most electronegative, right? Let's look at an example of a molecule and let's talk about hogging. Instead of saying attract, I like to say hog electrons, right? Let's use HCl as our example, hydrogen chloride. So, firstly, let's look at the electronegativity of each one of these. Hydrogen, the electronegativity for hydrogen is 2.1 and that for chlorine is 3.0. So let's write that down. 2.1, 3.0, right? Which means chlorine is more electronegative than hydrogen, right? So something to remember, your hydrogen and your chlorine bonded here, this bond that constitute two electrons really create what we call an electron cloud. And I'll use this to represent the cloud, right? But here's what happens with your electron cloud. Because chlorine is more electronegative than hydrogen, more of the electron cloud is pulled towards chlorine, more of it is over this side than it is by hydrogen. What that does, because more of the electron clouds is this way, being pulled this way, it induces a slightly negative charge on your chlorine, which is represented by sigma minus, right? This is an induced charge or what we call a partial negative charge. All because, electrons are negative. So if I push them this way onto the chlorine, you induce a negative charge. Clearly, too, if I'm moving the electron cloud or hogging it, chlorine is hogging it, taking all of it, it's going to induce a positive charge here. Just think of moving negative. You're moving something negative here, you're going to induce a negative charge. And if I'm moving the negative away from the hydrogen, you induce a slightly positive charge, right? Sigma plus. So hydrogen chloride, the chlorine has a slightly negative charge or what we call the induced negative charge, right? Or a partial a partial charge. And this is an induced positive charge or partial positive charge. Now, this is completely different from a negative charge that is on an anion. This is a full negative charge, right? This right here is a full negative charge. remember, Cl minus is formed by the gain of an electron. You have to realize that your partial or induced charge was resulted from the electron cloud being pulled, right? The electron cloud is being pulled this way, but it's still shared between the hydrogen and the chlorine. Is just that most of it is here. So that's the difference between a partial negative charge and a full negative charge. In this full negative charge, because I don't want you to get this confused, a full negative charge is a result of the gain of an electron. With the partials, it's from a covalent bond where the electrons are shared, but because one element is more electronegative, most of the electron that is shared between these two lies on this atom. So electronegativity is really important, right? It really will help when you start reactions with all the functional groups. And we're also going to use it to determine types of chemical bonds in a molecule.